Hi, I'm Jonaki Ghosh and welcome to my series of videos on teaching calculus using GeoGebra. In this short video, we are going to explore a very popular optimization problem known as the open box problem, in which we are going to use the concept of the derivative and the first and second derivative tests to solve the problem. First, let me tell you what the problem is about. So I'll take you to a PowerPoint slide. There is a rectangular sheet of paper, suppose it has dimensions 15 by 8 inches. Squares are to be cut out from all four corners and the remaining sheet is to be folded so as to form an open box. So what should be the length of the square to be cut out so that the volume of the box is maximum? Now let us see a diagrammatic view of this problem. Suppose this is a sheet of paper of length 15 inches and width 8 inches. I need to cut out squares of equal length from all the four corners so that the sheet now looks like this, and the sides are going to be folded up to form this kind of an open box. Now clearly, of course, the question is asking what should be the length of the square to be cut out so that the volume of the box is maximum. Now when you analyze the problem, you would realize that the length of the square to be cut out is actually the height of the box. The width of this box will be 8 minus 2x because there are 2 x's cut out from both the sides, and the length of this box is going to be 15 minus 2x. So let us try to analyze the problem and visualize it using GeoGebra. So now I'm going to open a GeoGebra file, remove the grid from the graphics view, and in this video we are going to explore the problem using the CAS window of GeoGebra. So I'm going to close the algebra view and bring in the CAS view. Now in the CAS window we can enter commands, and we can also do a lot of the computational work can actually be done in the CAS window. So now I'm going to enter the volume function v of x as x times 15 minus 2x into 8 minus 2x. So when I press enter, what I get to see is the GeoGebra has accepted the function and has done the computational work of multiplying, and we get a cubic. The volume function is actually a cubic function. It has also plotted the graph. But I do need to adjust the graph, so that I am going to adjust the y-axis and maybe drag the x-axis a bit. And broadly, this is what my function should look like. If you like, you can also do a right click on the function, go to object properties, and maybe change the color to a brighter color. And as you can see that the volume function, this is the volume function, a cubic function. Next, I'm going to I'm going to calculate the derivative of this function. So I'm going to say f of x is equal to the derivative. I'm going to use the derivative command, which is actually the derivative of the volume function with respect to x. So I don't really have to calculate the derivative myself, and GeoGebra is going to do it for me using the derivative command. And when I press enter, I actually get the derivative function, and it has also plotted the derivative, which is this green function. Once again, I can do a color coding by right clicking on this graph and going to object properties and changing it into a blue graph, a bright blue color. So my red graph is the volume function and the blue graph is the derivative function. Now I'm interested in these points where the derivative function cuts the x-axis. So what I'm going to do is I'm going to solve f of x for x. So let me say use the solve command. So I'm going to say fx equal to 0 for x. And let us see what GeoGebra gives us. Interesting. So it gives us the values of x as 5 by 3 and 6. So this point is approximately 5 by 3 and this point is 6. These are the 2 points where the graph cuts the axis of x. And now I'm going to identify, if I really click on this, notice that if I click on this, it gets converted to 2-point coordinates on the x-axis and the coordinates are also marked. Now I would like to know what is the value of the volume function at these points, because these are the critical points and obviously these are also the points of local maxima and local minima. So at x equal to 5 by 3 comma 0, the function has a local maxima, and at x equal to 6 comma 0 it has a local minima. But remember that my x represents the length of the square to be cut out. So clearly that length cannot be 6, because if it is 6, then you really can't do that, because the width of the paper is 8 inches. So therefore I'm only interested in this point, which is x equal to 5 by 3. And I'm going to use the extremum command. So I'm going to find the extremum of v x. Let's see what it gives me. Right. Now I can see that at 5 by 3 the function value is this, and I can just press on the circle and notice that it will be marked here. So this is actually the maximum volume that the box can have. So what do we observe here? We observe that the derivative function cuts the x-axis at 2 points. These are the critical points, and the function, the original function, that is the volume function, attains its local maxima or local minima at these points. We are mainly interested in this point because at this point we cannot really have x as 6. So we look at 5 by 3 and we find that the volume has a value given by this. Now I would like to, also prior to, as the derivative function cuts across the x-axis, it changes its sign from being positive to negative. So the original function is increasing before this point and is decreasing thereafter. So this is a point of local maxima. Now I'm going to try and work out the second derivative. So I'm going to say g of x is equal to derivative of, let me say, f of x with respect to x. Let's see what GeoGebra gives us. So this is the second derivative, which is 24 x minus 92, a linear function, and the green in color. And I would like to know what is the value of this function at 5 by 3. So I'm simply going to input g of 5 by 3, and we see that this is minus 52. So the second derivative tells us that if the second derivative at a point is negative, then at that point the function has, at that critical point, the function will have a local maxima. So in this video, we have seen how we can use the CAS commands to visualize an optimization problem. But more importantly, what we observed in this video is the relationship between the original function, its first derivative, and its second derivative. I hope you found this video useful, and I look forward to your feedback. Thank you.